Hi everyone. The material that we're going to go through in this video is going to cover the beginning of chapter 7. Actually the first two sections. The chapter is called Exponential and Logarithmic Functions and Relations. And we're going to delve into functions that you are not really familiar with up to this point in time. So it's going to be pretty new material, which means it will be pretty important that you pay attention to everything I go through and write down any questions that you might have so we can talk about it together in class. The first section is called Graphing Exponential Functions. So within this section, we're going to discuss what an exponential function actually is and what the graphs of those functions look like. And also consider things like domain and range as we go through and discuss them. So the first thing that you need to get down in your notes, besides the heading of the chapter and the section, is the form of this exponential function. So we're going to talk about, first of all, what is an exponential function. And an exponential function is a function that fits the form f of x equals a times b to the x, where a and b are going to be numbers this time. So the variable that we're looking at, these two values, the a and the b, are going to be constant values. And our variables are going to fall in the f of x spot and the x. Remember, f of x represents y. So those are going to be the two pieces of the formula that are going to be able to change for this function. The value of a is going to be considered to be the initial value. So this number right here will be considered to be the initial value. That occurs when x is equal to 0. So we'll have an initial value when x is equal to 0. The value of b is the base of the exponent, and for general purposes, b has to be a positive number. So it's got to be a number that's greater than 0. And then we have two scenarios. If b falls between 0 and 1, so it's a fraction between 0 and 1, we have what we call an exponential decay situation, or an exponential decay function. And we'll talk a little bit more about what that means here in a second. If your base, that b excuse me, is greater than 1, we have what we call an exponential growth situation, or an exponential growth function. So you need to make sure that you know what the general form for this function is, just like you know for a quadratic, f of x equals ax squared plus bx plus c. You need to know that the generic form for an exponential function is f of x equals a times b to the x. There are going to be times, even within this video, I'm going to do some application application problems that will vary the formula up a little bit, but this is the most basic generic kind of skeleton form of an exponential function. I'm going to ask you one question, and you see that question written at the bottom of the screen here. Why can't b be equal to 1? You notice that I go greater than 0, and then I also go around that value of 1. I'm going to leave that for you to think about between listening to this and when I see you for next class, and we'll have a short discussion about that at the beginning of the class period. But think about why b can't be equal to 1. I'm going to take this off the screen. Make sure you write down your questions as we move on to the next part of this. So we're going to start off with exponential growth, just because most of us think kind of in a positive way. So we're going to talk about what the function looks like and the different pieces of it. So an exponential growth function, the generic parent function, would fit the form f of x equals a times b to the x, where b is greater than 1. Now, a lot of times in kind of our basic functions, the a value is equal to 1. So you may just see written down f of x equals b to the x. It's implied that the initial value then would be equal to 1, which means that when x is 0, we have a starting point of 1. And we'll talk a little bit more about why that happens in class as well. Just if you want to consider it, if x is equal to 0, that makes the exponent 0. b to the 0 power is equal to 1. 1 times a would give you a, which means that our initial value will be whatever that value of a is. But like I said, we'll discuss it a little bit further in class. I'm going to have you put a few descriptors down as far as the type of the graph goes. We're going to call this graph continuous, and that means it has no holes in it or gaps. We're going to call this graph 1 to 1, and we talked about that earlier in the year, about what that actually means, and the fact that 1 to 1 means it passes both the vertical and horizontal line test. For every domain value, there's one range value, and for every range value, there's one domain value. And then it's also considered to be an increasing function. That means that as the x's go up, the y's also go up. The domain increases, the range increases, kind of thing. If the domain decreases, the range also decreases. But we consider it to be increasing because we go from negative infinity on the x-axis towards positive infinity. The domain for these exponential growth functions are always negative infinity to positive infinity. And the range will always be from 0 up to positive infinity, exclusive of 0. We'll never actually reach a y value of 0. So it's going to kind of carry along the x-axis. We have what's called an asymptote, and an asymptote is a line that's not part of the graph, but it's kind of like it could be vertical, horizontal, or kind of on a diagonal, that the graph is going to run along. So we call this asymptote y equals 0 in this case, and I'll show you where that is. And then we have one intercept, and it's a y-intercept. That's going to go through the point 0, 1. So every exponential growth function goes through the point 0, 1. If I wanted to generically graph something that would represent an exponential growth function, this is what it would look like. I know it's got to go through the point 0, 1. And if I'm just working off of this f of x equals b to the x, when x is 1, y is always going to be equal to b. So pretend the grid isn't here for the time being. I'm just going to put the next point at an x value of 1. There's my x value of 1. And I'm going to say that b will be right here. So the point 1b will always fall on the graph. And then the point -1, which I'll make right here, 1 over b will always fall on the graph. So my exponential growth function kind of looks like this. It looks like it's horizontal along the x-axis, but it's really not because it gets so minutely close to it, we can't really graph it very well. But it resembles this. This is y equals b to the x. I'll do it with a concrete function on the next screen, but you need to show that as the x values increase, as they go this way, our function increases, what we say, in an exponential way. It grows bigger very, very, very fast. So this is a general form, general shape of a graph for an exponential growth function. I'm going to go over to the next screen, and I'm going to do one that's a little bit more concrete for you. So we'll put some numbers to it. This is the graph, or I want you to look at the graph of f of x equals 3 to the x, and then talk about the domain and range. So based on what I just said, this is my base of 3. Because it's larger than 1, I know it's exponential growth. And then I'm going to take a few of the things that we talked about in the previous screen into consideration. We know that the graph will always pass through the point 0, 1. So I can put my intercept there. Now, excuse me, for an x value of 1, we know that we have the point 1 comma b on the graph. My b value is 3. So I know that the point 1, 3 falls on the graph. And think about that. If I put 1 in for x, I have 3 to the first power, which is 3. I also know that I have the points -1, 1 over b. So at -1, I'm basically at a y value of 1/3. So that's giving me the basic beginning shape of the graph. I might plug an x value of 2 in just so that I can kind of confirm the shape of the graph. That'll bring me up to 9 because 3 squared is 9. And if I were to go in the opposite direction, if I put -2 in, that gives me 1 over 3 squared, which is 1/9. So you notice that my graph starts to get really close to that x-axis. I can't even keep it away from the x-axis with my marker here, so it looks like it's touching, but it will never actually touch or cross that horizontal axis. So I'm going to connect my dots. And this is the graph that resembles y equals 3 to the x. We can call it y or f of x. Now, the bigger the base, the bigger that value is, the higher it is over 1, then the steeper the graph you're going to get. The domain and range, though, is always going to be consistent for every single one of these. So negative infinity to positive infinity, and 0 to infinity, respectively, for domain and range. So you should be able to graph these with not too much difficulty. When you get into class, I'll show you how to use your calculator in order to graph them as well. We're going to look next at an exponential decay function. So the graph of that, because we said that an exponential growth function was always increasing, an exponential decay function, you can probably guess, will always be decreasing. So this time our parent function doesn't look any different generically. It's still f of x equals a times b to the x. But this time our b value falls between 0 and 1, exclusive of those values. Again, often a is 1, so you might see this. It looks the same, but you have to put those criteria of x being between 0 and 1 on that if you're going to work with decay. This, again, is considered to be a continuous graph. It's still 1 to 1. And it, what's the other one? It's this time, instead of increasing, it's decreasing. The domain is the same as the one of exponential growth, negative infinity to positive infinity. Its range is exactly the same from 0 to infinity. It has the same asymptote, so it runs along the x-axis, and it has the exact same intercept. So really, the only change here is that it's a decreasing function because our base goes between 0 and 1. Now, generically, if I were to look at a graph, actually, we can do it. Why don't we do one that's a real graph? Well, let's do y equals 1/2 to the x, or y equals 0.5 to the x. Those are the same. You might see decimal form, you might see fraction forms. We know it's going to pass through the point 0, 1. I know that I have the point 1 comma b on my graph. So 1 comma 1/2 would be about right there. My marker is so thick that it doesn't look like it's 1/2. And then I also have the point -1 comma 1 over b. Well, if my b value is 1/2, what is 1 over 1/2? 1 divided by 1/2 is the same as saying 1 multiplied by 2 over 1. So that's equal to 2. So at -1, I have a y value of 2. So there's my template for my graph. If I do a couple more points in either direction, if I try -2, if x is -2, 1/2 to the -2nd power is the same as 2 over 1 to the +2nd power. I can take my exponent rules into account and say that's 4. So I will have the point -2, 4, and then I'll have the point +2, 1/4. So we're getting closer to the x-axis. My graph here, my dots, looks something like that. Y equals 1/2 to the x power. I probably should put parentheses so I know that both are being raised to that power. And you can see that as the x values get larger, the y values get smaller, and this would be considered to be a decreasing graph, as opposed to when we had the increasing with the growth factor. So again, you need to make sure that you can recognize exponential growth and decay. If you saw the graph, you should be able to give me some characteristics of the graph and go from there. But we're going to do some practice with this in class to make sure that your understanding is apparent. This next slide is going to give you a variation of the exponential formula. And this formula that I'm going to give you is a of t equals a times the quantity of 1 plus r to the t. Exponential functions often model a lot of real-world situations, things like population growth, half-life in science class. You may have talked about half-life in biology. So sometimes we have to kind of dissect the formula a little bit more from its base. So this version of it, a of t equals a times the quantity of 1 plus r to the t, can help us still model exponential growth and decay when we know what's called a constant % increase or decrease over time. So if we have a problem that talks about percent increase or percent decrease over a period of time, then we can kind of move into the formula that we have in front of us. Now the A of t represents the final amount after the period of time passes. The little a is the initial value, so that's not changing. Sometimes we'll refer to it as the initial amount in these types of problems because we're usually talking about an amount. The r value, which is new, because our base is no longer just b, it's become 1 plus r. 1 indicates like the whole, the starting point, 100% kind of thing. And then we go either up or down. So r is the percent increase, which would be a positive value, or decrease, which would be a negative value over the time period. And you'll see what I mean by that when we do an actual problem. T is our time. And the entire quantity 1 plus r is known either as the growth or the decay factor. If r is positive, then it's considered to be growth. And if r is negative, it's considered to be decay. So think about if we start with our whole and we're adding something onto it, we're growing. If we start with our whole and we subtract something from it because it's negative, then we're decreasing it or decaying. So it's important for you to know this version of the formula, know what the components of it mean so that we can apply it in an actual realistic problem, which we're going to do here in a second. So let me know if you have any questions about the pieces of that. Let's move to the next part. And we're going to see how this can be actually applied. This problem reads, the first U.S. Census was conducted in 1790. At that time, the population was 3,929,214. Since then, the U.S. population has grown by approximately 2.03% annually. Determine the exponential function that models this data. So when I want to determine an exponential function like this is saying, and I know that a percent is mentioned, I'm going to try to fit that formula, a of t equals a times the quantity of 1 plus r to the t power. And I need to kind of find the different components of that formula within our problem. The total amount would be the total population. Now, we don't know what that is. All we know is that it's increasing, it's growing. And the initial population that was discussed in the problem when the U.S. Census was started in 1790 is 3,929,214. So that's our a value, our little a value. Let's think about what the growth factor is going to be here. We know that it's going to be growth because of the grow. It says right in the problem that it's growing. Growing by 2.03%. Now the r is the percent of growth or decay that we have given to us in the problem. We always use it as a decimal. It will be given to us as a percentage. You have to change it to a decimal. So that's going to leave us with 1 plus 0.0203 to the t, which in the end will give us a formula of 3,929,214 times the quantity of 1.0203 to the t power. This formula, which we're calling a of t, is the formula that would model the information, the data given to us about the U.S. Census that's been conducted since 1790 with a constant growth rate of 2.03%, knowing that the initial population was 3,929,214. So you should be able to develop a formula that will model exponential growth or decay for any type of data set that's given to you. We can, again, talk a little bit more if you have confusion about where any of the values are coming from when I see you in class next. I'll model one that shows us decay here next. Green tea. I don't know if any of you guys are green tea lovers. I'm not a huge fan. I think it's bitter. But anyway, a cup of green tea contains 35 milligrams of caffeine. The average teen can eliminate approximately 12.5% of the caffeine from their system per hour. the first thing you need to do is determine the exponential function that models the data. And secondly, you need to estimate the amount of caffeine in a teenager's body 3 hours after drinking a cup of green tea. So coming up with the formula, we're going to do something very similar to what we just did. A of t, you might have to write this down a little bit before you start to learn it, equals A times the quantity of 1 plus R to the t power is the version of the formula that we'll use. This time, I'm going to keep in mind that we're eliminating the 12.5%, so that's going to tell me decay. So my R value is going to need to be negative. A of t will equal, every cup contains 35 milligrams. 35 times the quantity of 1 minus 0.125, that's our 12.5% as a decimal, to the t power, which leaves us with A of t equals 35 times 875 thousandths to the t power. This is our equation that models the decay that's going on in that problem. We know it's exponential because the variable is in the power. I also know this is exponential decay because that value that became our base is a number between 0 and 1. Now, part B asks us to estimate the amount of caffeine in a teenager's body 3 hours after drinking a cup of green tea. So what are we trying to solve for? If this is our formula, we now have two variables. Here's one variable. Here's the second variable. A of t represents the amount, and t represents time. So I have information about time, which I can plug in and find A of t. So my work for this will look like this. A of t equals 35 times the quantity of 0.875 to the third power. And you will go to your calculator. I'll demonstrate if I can find my cursor. Here it is. To turn it on, I'm going to say 35 times the quantity of 0.875. I'm going to use my caret key for my exponent to the third, and we will get an answer of approximately 23.447. So if I go back to my other screen, I will say that there will be about 23.447 milligrams of caffeine left in the teenager's body after 3 hours of drinking a cup of green tea. So some of this is going to be calculator use as we get a little bit further into it, so we'll kind of work together if you have issues with punching the values in. Sometimes that becomes a little bit of a problem for some people. All right, let me know if you have any questions on that. That basically covers what's in the first section of chapter 7. Identifying the type of function that you would have, knowing what they look like, and then creating a function. Now the second section delves into actually solving exponential equations and inequalities. So I have two things put up on the screen here. One is an equation and one is an equality, or an inequality, I'm sorry. I want you to think about them for a second. The first one says 3 to the x equals 3 to the 5th. And remember, if we're solving an equation, which this is, we need to find the value for the variable that's in the equation. If 3 to the x has to equal 3 to the 5th, hopefully you're all logically thinking that x would be equal to 5 because it would make the left side equal the right side. So the rule of thumb with solving exponential equations is that the first thing that has to happen is you have to make your bases the same. So bases need to be the same. And once that happens, in this problem we didn't have to manipulate anything, but we will in the ones that I give you in a little bit. Then once the bases are the same, all we have to do is set exponents equal and solve. So you basically forget about the bases after the fact. Once you set them equal to each other, it's almost like they're not even there, and our new equation becomes the two exponents equal to each other. The same idea is going to happen with the inequalities. If 2 to the x has to be greater than 2 to the 6th, then we know that x has to be greater than 6. So we're going to follow the same idea as with solving equations with inequalities. It's really not rocket science. The hardest thing is going to be to figure out what the like base will be if the bases are not the same in the original problem. So let me show you a couple to see what you think about them. 2 equations and 1 inequality for us. And our goal is to solve the equation or the inequality that's presented to us. The first one is 2 to the x equals 8 to the third. Now, the way that this is presented to us, I can't jump right in and, and say x is equal to 3. If I tried to do that, I would get 2 to the third, which is 8. 8 doesn't equal 8 to the third. 8 is just 8 to the first. So we have to create like bases. You have to think about what a like base would be. Now, 2 I can't write any other way. So I'm going to have to leave 2 to the x alone. But I do know that 8 is 2 cubed. So I've now taken the base, the original base of 8, and written it as 2 cubed. That's still being raised to the third power. So my new problem becomes 2 to the x equals 2 to the 9th once I apply the exponent rules of multiplication there. And now since my bases are the same, I can say x is equal to 9. And you can kind of double check that on your calculator if you wanted 2 to the 9th is equal to whatever 8 to the third is. So that's our final answer. The second one, 9 to the 2x minus 1 equals 3 to the 6x. Can we write this with like bases? Now, there may be a situation where you can't use a like base. And we'll delve into that a little bit further in the chapter. But right now, everything should be able to be rewritten with like bases. When I look at this, I think of 9 being 3 to the second power. So 3 to the second is going to be raised to the 2x minus 1. And 3, because I just rewrote that as a base of 3, can be left as 3 to the 6x. Bases are gone, and this becomes 2 times the quantity of 2x minus 1 equals 6x. 4x minus 2 equals 6x. Negative 2 equals 2x, and x will be equal to negative 1. So once you get those bases, like it's just like solving a very basic algebra 1 type of equation. The third one's an inequality. So in this third one, I'm going to create like bases. Now, 16 and 8 are the original bases. I can't write 16 as 8 to something, so I think I'm going to have to look at changing both of them. But a base that can be used for both of these numbers is 2. 16 is 2 to the 4th, and 8 is 2 to the 3rd. So once my bases are the same, I'm going to have 4 times the quantity of 2x minus 3 is less than 3. 8x minus 12 is less than 3. 8x is less than 15, and x is less than 15/8. So my inequality is solved. Now I'm going to write this from negative infinity up to 15/8 because we like to use integral notation in our final answer. So it's not too tough. Like I said, the hardest thing is going to be figuring out what base to use for some of the problems. And as you do more of them, you'll get more used to thinking about things in terms of like bases. We're almost there, guys. I'm going to give you a word type problem. This one's going to be a little bit more thought-provoking than some of the others that we did. It reads, Kristen starts an experiment with 7,500 bacteria cells. After 4 hours, there are 23,000 cells. Write an exponential function that models the number of bacteria after X hours if the number of bacteria changes at the same rate. So the fact that we're told that the bacteria changes at the same rate tells us that I don't have an actual R value, so I'm going to just use a base of B, knowing that there is some type of constant change. What do these numbers 75,000 and 23,000 have to do with? Remember, here's my generic function. F of x equals a times b to the x. And I used a different version of that when I used a of t equals a times 1 plus r to the t. But we said 1 plus r is really just b this time. We are talking about time, so it's kind of like we're working with the second version of this, but the problem says use the variable x instead of t. So I think I'm going to rely on this formula here first. The 7,500, it says it starts with 7,500, so that's my a value. So I know 7,500 is going to go in for a. Do I know b? Are we told the base? Because we don't know that rate, that change of the percentage change, I don't know B, and I know that X has to stay as a variable. The 23,000 then is what we end up with after 4 hours. Although, I shouldn't say I don't know X. I do know X to be 4 in this situation. I'm going to erase more than I wanted to. So I'm going to fill that in with a 4. Now, this is not a generic formula because the generic formula has the f of x and the x left alone. But I can use this to find b and then rewrite. So if I want to try to solve for b, right now I've got to isolate b to the 4th. B to the 4th is equal to 23,000 divided by 7,500. I could take a couple zeros off of there. So b to the 4th is equal to 230 over 75, and I can probably reduce that even further. But you know what? I'm going to say that b will be equal to the 4th root of 230 over 75 and get that on my calculator. So if I pull up my calculator, I need to do the 4th root. I have a couple options here. I can either type in 4, my calculator is a little older, so I have to do it this way. 4 and then number 5 after I hit math. That will tell me the 4th root of, what was that value? 230 over 75. So in parentheses, 230, whoops, divided by 75. Close my parentheses. Which equals about 1.233. Now another option I could have done is 230 divided by 75 to the 1/4 power. Remember, because we know our rational exponents, we can also, instead of taking the 4th root, do that. So your option, you see we get this exact same value. So if I go back to my notes, I'm going to say that b turns out to be about 1.233. That means that my generic formula can read, let's do, maybe we'll call it a of x so that we have the a in there for amount. A of x equals the 7,500 is our initial amount. That has to stay in the formula this time. That's the little a. Times 1.233 to the x power. By reading this, I know this is exponential growth, and I know that the amount went up. I can also interpret the 1.233 tells me that there's a percentage change that's constant of 23.3%, because that's the extra value that got added onto the 1. As a decimal, 0.233 is 23.3%. The question that's asked of us in part B, though, this is our generic formula now, is how many bacteria can be expected in the sample after 12 hours. So I need to look at A of 12 and plug in 12 for the X. And if I do that and go to my calculator, I'm going to have 7,500 times 1.233 to the 12th power. And that will give me, oh, did I write that wrong? Was it 323? 1.323. I think I wrote it wrong, so let me bring that back up. Let's go back in here. Let me just start over again. 7,500 times 1.323 to the 12th, which is going to give us about 215,664 bacteria. We're not going to include the decimal in it because we need a whole bacteria in order to do this. So my final answer for this problem will be that 21,000 or 215,664. This was 323. I wrote it backwards right from the beginning. You guys were probably yelling at me. So I'm going to say about 215,665 cells of bacteria will be my final answer. Again, writing wrong, 665. So this one's a little bit tougher because you have to solve for that base before we get into the problem. But once we do that, we're pretty much okay. This might be one that we have to go through again together when I see you in class, and that's perfectly fine if that is the situation. We're really closing near the end here. I think I have one or two left. One idea and then one problem. So there's a third version of this formula that we're going to look at. And this third version involves what we call compound interest. So these are the money type of problems. If you have something that involves compound interest, this is the version of the exponential formula that you need to use. A equals P times the quantity of 1 plus R over N to the NT. Now, A is the amount earned in an account or whatever your investment is about. So the amount earned. P is the principal. So that's in the place of the initial value. That's what that means. It's the amount of money that you start with. So that's the financial term of initial value, principal. R is the interest rate, the annual interest rate. And this is always as a decimal, not a percent. N is going to be the number of compoundings that occur within the problem. And I'll show you what that means when we do the actual problem. And T is time in years. So here's a third formula that you need to know, but it's just another version of the base one. You need to know what each component means, again, so that you can use that in order to solve given certain data. So we will go to the last problem and look at this. It's not going to be too difficult. This says an investment account pays 4.2% annual interest compounded monthly. If $2,500 is invested in this account, what will be the balance after 15 years? So we need to pull out some important pieces here. We know that we have an annual interest rate of 4.2%. We know that interest is compounded monthly. So that means 12 times during the year. So when we talk about the compounding, we want to think about how many times per year that's happening. The $2,500 is invested into the account. So that's how much we're starting with. We want to know what the balance will be after 15 years. So let's look at our formula. Our formula is A equals P times the quantity of 1 plus R over N to the NT. Now, what do we know? The 4.2% is our R value. We're going to write it as 0.042. That's going to go in for R. Compounded monthly tells me that N is equal to 12. 2,500 is my P value, and 15 is how much time has passed. So if I take that information and I plug in, the one thing I don't know is A, and that's what I'm trying to find out. So 2,500 times the quantity of 1 plus my interest rate of 0.042 over my compoundings, which is 12 per year, to the 12 times 15th power. I need to put this in on my calculator in order to get a final answer for this. So this, again, may be one of the tougher things for a few of you to do, but I will help you when we work on these problems in class. So our work is going to look like this on our calculator. 2,500 times the quantity of 1 plus the quantity of 0.042 divided by 12 to the, in parentheses, 15 times 12 or 12 times 15 Doesn't matter the order of those numbers. And then hit enter. Well, okay, it didn't give me the right answer, guys. What did I do there? That looks right. Let's try this again. Did I put the wrong numbers in? 2,500. I'm telling you, you guys are going to have difficulty with this. Times the quantity of 1 plus, in parentheses, 0.042, because that's my 4.2%. Divided by 12. Did I not double parenthesize this? To the, in parentheses, 12 times 15. Knock that down, enter, there I go. Okay, I think I dropped a parenthesis, so that's a lesson learned for me. The answer I get is $4,688.87. This is going to be one instance where you do have to go to only 2 decimal places because it's a money problem. So you're going to tell me the amount in that account will be $4,688.87. Dollar sign always goes before, please don't put it after. Okay, a lot of material in there, using 3 different versions of the base formula. When you come in, of course, I will take questions from you. We will do practice problems, and we'll kind of see where things stand. So thanks for listening. I appreciate the fact that you took good notes on this, and looking forward to our conversation in class.